Okay, so hi everyone, and welcome to week 3 of our journey for the certification for machine learning engineer. My name is Fatio Callahan. I'm a full stack engineer and a tech lead at Charles River Laboratories, and you can follow me on LinkedIn and on my Twitter account. I'm a computer scientist with a background on artificial intelligence, and yeah, I'll be more than happy to review all of this content with you. And yeah, let's begin. Okay, so here you can see all of my amazing colleagues on this journey. And all right, so again, this is very similar as the previous sessions. We're going to see where are we on our journey through all of these study groups. We're going to do the review for the exam guide. We're going to have a quick look to some sample questions, and then some Q&A, and open, of course, to listen to all of your comments. And then we will see what are we going to do for the next week. All right, so where are we on our journey? So we are in week 3. So today, we're going to be talking a lot about feature engineering. You have some resources that you can also follow along apart from this session today. And there's also a hands-on lab practice, which is really, really nice. And yeah, I highly suggest you to do it. Because it talks about explainable AI, which is a really nice topic and very useful. It's very important for us to understand what is it about. Okay, so what are we going to be seeing today? So we're going to talk about everything related to the preparation that we have to do with the data that we're going to use to train the model, to test the model, and also the processing. So we're going to talk about the data ingestion, data exploration. We're going to have a look at how we can design the pipelines, and we're going to also talk about the feature engineering. Um, so, for example, yeah, like our key concepts are data ingestion, best practices with the architecture, um, how to deal with missing data or with data sets which can have imbalanced classes. We're going to talk a little bit about that later during this session. And Sarah, since I'm using just my laptop, I don't have my usual lots of screens. So if there is something on the chat that is worth mentioning, please unmute yourself and let me know if I should go to the chat. Okay. All right. So this is the process. Let's say it's the machine learning whole process. And of course, in practice, this is not a linear process. So in this diagram, we can see all of the steps on the whole machine learning, say, the journey, all right? So first we have to define the machine learning problem. And of course, if the problem that we want to solve can be solved with machine learning, because let's remember that machine learning is not like the one solution for everything. There is a lot of people, a lot of companies that they just want to throw machine learning because it's like the shiny thing nowadays. But we have to analyze the problem and understand what do we want. And if machine learning is the solution to it, then we have to define the problem and propose the solution and then start working on it. Then you have to construct your data set. You have to do some transformation to the data. Then you have to train the model, of course, and then you're going to use the model to make predictions. But this is a very, it's just a summary of different steps that we need to do to go from the very beginning until we can finally use our model. So today we will be focusing on constructing the data set and in the transformation of the data. Okay, so with this in mind, let's think about this question. So if you prioritize improving one aspect of your machine learning project, which will have the most impact? So we can be using the latest optimization algorithm. Um, we can talk about the quality and the size of our data, training data or test. Maybe we can use a deeper network, or maybe a more clever loss function. So I guess we can all agree that option B is the correct answer. The quality and the size of their data is obviously the one that has the most impact, because you might have a nice infrastructure and you prepare the model to do the predictions like in the best way possible. But if your data, if your training data is not big enough, it's not diverse enough, and the quality is poor, maybe we have some imbalance between the classes, the model will never output correct prediction. So this is definitely um, the option that has the most impact. For that reason, again, the topics that we're going to talk about today and are really important, and they are a crucial part of the process. In the step related to constructing the data set, we have several tasks on it. So first, we have to collect the raw data to work, let's say, we want to create a model to predict for how long a bike is going to be rented. We need to collect all the existing data to be able to train our model and go through the whole process. Identify the features and the label sources, because we need to obviously have different features on our data to be able to do, let's say, if it's a classification problem, and also label that data if we're using, supervised learning. Um, then we have to select the sampling strategy. So, for example, if you try to build a classifier between two classes, and the classes are heavily imbalanced, for example, one class is bigger than the other, obviously that is going to affect directly the results of our model. So maybe what we need to do is to, for example, undersample the bigger class to get a better balance, or uh, give more sampling to the smaller class. So depending on the case of what you want to do, you have to try to find a good balance. And that is just a part of the sampling strategy. So you have to think about that kind of issues. And then, well, splitting the data, that is about getting some data for a training, let's say for the training set, some data for a testing set. But that really depends. The way you select which data is going to be part of the training set and which data is going to be part of the test, it depends on what you want to do with your model. Okay, then the other step will be transform the data. So of course, how to in the data that we are using, and also the feature engineering that we're going to see a little bit more about it in the next slide. Okay, so these are the kind of questions that we need to ask ourselves while thinking about our data. So first, do we have enough data? Um, Obviously, the biggest, if the sample is bigger, we can get a better model, again, depending on what you want to do. And also the data is high quality. So those are questions that we need to ask ourselves. So we have a good input. If we have a good data as input to the model, we're going to have a good output. And of course, on the other hand, if we have a bad input, we're going to have a bad output. Um, so just some real examples of where this can go wrong. I don't know if you have heard of Amazon once they were using a model to select CVs, right? And they were training. They created the model. They trained the model, and the result was that the model was discriminating against. So most of the time, it would select CVs from male engineers, and obviously that was a scandal, and it's a very horrible example of machine learning going wrong. And the issue was that, of course, the model was doing what it was trained to do. And the thing was that the training data was almost it was almost fully about male CVs. So you have to be careful how you collect your data and how you classify it and everything, because otherwise you can have this horrible. There's another example. There is a country that was using a passport application online, and a couple of and then that application would check the picture. So you know that for passport pictures, you need to follow some. You cannot have a background, like the background has to be white. You cannot wear hats, and so on and so on. So the system was rejecting the application, for example, of a guy that he was using a wheelchair. And because in the picture, in the background, you could actually see the wheelchair, and was just rejecting and rejecting the application because the picture was invalid, right? So they tried to, call he and his family, calling, and it was like a nightmare of a process. And the only thing that worked for them to be able to the application was that his parents, they need to stand behind him and grab him on the back. He was outside the out of the wheelchair, so they had to grab him on the back and like hide behind him and try to to support him for him to be able to take the picture. With the same application, there was also and then it worked, right? Because the background, the wheelchair was not there anymore. Then with the same application was another issue. But this time it was an Asian guy, and the application keep on rejecting the picture under the reason that he needed to have his eyes open. And of course, it was because he was an Asian guy. So as you can see, these horrible examples, they are the consequence of not having uh, diverse data and enough data to properly train these models. So this is something that all of us, we need to be very careful about, and just think about all of the cases that can be part of your model that the model want to predict, and think about, maybe don't just use the data that makes sense for you. Think about all of the different possibilities and characteristics that follow. Okay, so because of that, and more other reasons, we really need data validation. And well, usually in software engineer, like let's say the classical software engineer, the behavior of the system is defined by code, by the code that we write as programmers. And we can validate how the system functions using unit tests and other bunch of different tests depending on what you're writing. So we can beforehand, if of course if we're writing good tests, we can be sure beforehand that, okay, the system is going to work as expected. But the issue with machine learning is that the behavior of the system is defined that we use to train the system. So think about the examples that I told you before, right? And then you can understand, okay, how the model behaved when the data was a little bit different, not as expected. So how can we really be sure um, and be confident of the output of our model? So we really need to have a way to validate the functionality. But this is not code. This is we're using just data from the sets. So what can we use to validate the infrastructure that we set up that is going to work? So we will look at the data validation step, which is part of the machine learning pipeline. So we would look at the TensorFlow extended as a solution to build this kind of pipelines. And it consists of a number of different components. So we have the integrated front end, and then we can monitor the pipeline, the job management, the debugging. We can visualize the data, the model, the evaluation as well. Then we have the shared framework and job orchestration for your jobs. And then we have different pipelines components. So we have the data ingestion, how are we going to feed the model with the data, and and when I say data, is all of the data that we use, the training data, the test data, and so on. Then we have the TensorFlow data validation. We're going to talk about that. We have TensorFlow transform, and that will help you transform the data into feeds that will be used to train the model, and it is going to then transform those features into a format that is useful for the model. So I want to have a look at the TensorFlow validation. So the TensorFlow data validation is a tool that works with TensorFlow, and it helps you analyze your data and provide some high-level metrics on the data you're going to train the model on. And it can be used to analyze very large data sets and do continuum monitoring. For example, the new data that you collect. So again, it will help us understand, validate, and monitor the data. We can analyze and validate. It can be used to analyze and validate a lot, like really large amount of data. It has a proven track record that is very, very useful to check that everything on the production machine learning pipelines is everything is working as expected. So it's a very, very, very good tool. So now we are going to watch a video, having a look at it, and I'm going to talk a little bit about it. So this example is the Chicago taxi trips dataset. And this is one of the public BigQuery datasets. So yeah, basically what we're doing here is connecting to the BigQuery dataset, and we are running a query to pick certain, I'm gonna be stopping this to explain it a little bit more. Okay, so what we want to do is to collect a lot of data from this particular data set, and we're going to run the query, and we might load the data set in CSV files, and then after that, we're going to be able to see, well, this is all of the information that we fetch, right, from the data set. So we can see when the trip started, for how long was the trip, how many miles, how much paid, if there was some tips, the payment type, the company, and the latitude where the drop off actually happened. So this is pretty cool. The tool allows us to see all of these. Then we can have the compute statistics. So we need to load the data, right, on a certain location called train data. And then we call the TensorFlow data validation to generate the statistics from the SSB, from the CSV file, right? That's the way we are going to get all of the training statistics, okay? Then we can visualize the statistics, and it will show numerical data, and we can also see categorical data or the features, and they're going to be visualized separately with their distributions. So we are going to see like a little histogram to show how the values are distributed within a range. So if we in values, or if we have zero values, we are going to see like how much of that percentage is related to it, and we're going to see that in red. So that's good because we can visualize right away where are we having problems, and maybe we need to gather more data for that specific feature. Then we can expand the distributions to see them more clearly, and we can, hover over and then also to display more data, and switch between the scales for the payment type, categorical features. So what we need to run is on the TensorFlow data validation, we're going to run visualize statistics for that particular set, which is the training statistics. So let's have a look here. As you can see here, we can see all of the like the features, like the ones that are numeric, like fare, trip start hour, and so on and so on. So for example, you can see that the fare has 0% missing data, and the mean, the max, the median, and a lot of information that is very useful. Then, for example, we can see here that we have some 28% missing for the drop-off. You can see the distribution on the graphic on the right side of the screen. Okay, so then here, let me roll back a little bit. We have the categorical features. So of course that is a different way of treating that because they're not numeric, and we can see the same. For example, we can see that we have 100% missing data for the pickup census track. So we can spot right away. Okay, we might have an issue there. Okay, and then you can see that you can expand to see the graph. The pickup is completely empty, the payment type. So as you can see here, because it's a categorical feature, we can see the different categories: cash, credit card, no charge. So we can see how it is distributed for each of the categories. So that's pretty useful. Then we can check evaluation data for errors. So we have the statistics for the training data, and then we have the statistics for the evaluation data set, right? And we can use these to compare the statistics between the two of them, and we can we can say if there's an accuracy, and where is it? Is in which in if that happened in the training process or is on the evaluation data. So what are we doing here? We have included an evaluation data set now, and we have it here. So as you can see, we again use the TensorFlow data visualization, and then we're generating the statistics from the CSV that is coming from the evaluation data, and then we're doing the comparison, right? So we're comparing the evaluation data set against the training data set. And now we're going to check for anomalies. So the blue one is the evaluation data set, and the other one is the training data set. So we created an evaluation data set. Now the features, it has two values. Again, each feature has a value for the evaluation and another one, the orange is for the training data set. So this will allow you to compare the shape of the distribution across all of the different features. So we will need to have a look to check for the ones that look really, really, really different, right? For example, the fair one might look a little different, and so on. For example, the trip miles are also look very different. So that's one that we have to check. So let's see, it's going to be expanded probably to see in much better detail what's the problem. So you can see here that the difference is very important. So again, this is an amazing tool. Okay, then we can check for drift and skew. So it, different skews between the training and the serving data or drift in serving. So we can detect if there's any schema changes, see if there are statistical changes of a specific feature, if there is changes on the distribution of a feature, and then it can detect statistical changes of all the features between two time windows, like comparing it into different points in time. So that's also very useful. So basically what is being done here is that we take the train statistics, we take evaluation ones, and then the serving statistics. Then we compare them and validate them to find if there's any anomalies. So let's see what it found. This video doesn't have any sound, so that's why I'm explaining. Okay, so we can find then the results. So it found two anomalies, right? One in the feature payment type and one in company, right? So time type, there is a difference between the serving and the training data, and the value with the highest difference is credit card, and then in company, there is an anomaly between current and previous. So that's the serving status and the eval states, and the value with the maximum difference is Blue Ribbon Taxi Association. And that's it. So now let's look at data ingesting part. So for this, TensorFlow offers an input pipeline API. So why do we need this pipeline? So for example, maybe your data might not fit into memory because it's way too large. The data might require randomized pre-processing because of course we would like and we need to efficiently utilize the hardware. And the decoupled loading and pre-processing from distribution is because you want to make sure that your pre-processing is done in such a way that you can apply the same pre-processing when you are serving the data. So you're actually having a, you can make sure that is going to work the same as the data that you're serving is going to be processed the same way as you did when training and preparing the model. Okay, so for that we use TensorFlow.data, and that's the TensorFlow input pipeline. So basically what it does is we do some ETL process for pre-processing, again, the data that we're going to use. So for extraction, we can read the data from memory or from storage, and we can parse the file format, right? Depending on the format of where our data is being stored, we can parse it to um, be able to apply operations over it. Then we do the transform step. So again, depending on the data that the raw data that we're having, we might need to do some transformations to be able to use it properly. So we can do text vectorization, we can do image transformations, video temporal sampling, shuffling, and batching. And then we need to load the data, right? We need to load it to be able to process it, right? To work with it, and to the accelerator. So in that you see at the left, at the right, we can see the CPU and the accelerators. So the CPU during a lot of long time, the capacity and the velocity, the speed of a CPU was doubling, um, like in a very exponential way. That's kind of an exponential way. But then it kind of stopped, and it was following a certain law that stated that the CPU processing powers and the speed was going to duplicate like that every certain amount of time. But now, more recently, it has reached like a plateau, let's say. And on the other hand, the GPU, which is the let's say the graphic cards, are continuing like increasing their capacity and their speed of processing information. So that is very, very good if we want to process data and um, heavy computations, like the ones that are being used in machine learning. So it's like a very, very useful resource to use instead of just the CPU. But it really depends on your model, what is that you want to do, the size of your data. But yeah, that is something that is good to have in mind. Okay, so let's have a look at an input pipeline example. So for example, like, I'm not going to explain the code bit by bit, but yeah, this is just where we're using TensorFlow. We want to define the preprocess function, and we are first loading the data set, like we're determining like the way to map it, the batch size, and then we're going to start working with the model. You can see there, we're again reading data from storage. Then we are applying some user-defined preprocessing. And we're going to batch the data for training efficiency. And we're going to talk a little bit about that later in some next slides. And then we're training the APIs. So training the APIs natively support TensorFlow.data. Okay, so this part is really, really fun. So the efficient resource utilization. Okay, so if you can here, over time, we can use, okay, the CPU is going to prepare the data, and then like the first batch, and then it's going to become idle while the GPU is used to be to train that batch, and then prepare two, and then it's going to be idle. So as you can see, we're kind of using it, they're alternating the way. So over time, that can be like, it can take a certain amount of time. But then we can work in a more parallel way, if that makes sense. So if you see the graphic on the bottom, like the bar in the bottom, you can prepare the second part and train while you're training, while the GPU is training the first one. So it's obviously a most better, efficient way to work with this. But we can do much better. So we can actually do parallel transformation. So we can use the CPU to prepare and map, and then batch. So it's a sequential map. And then with the GPU, we can train, and then it will become idle while the CPU is finishing. And then you can use the parallel mapping, as you can see there. So the CPU can be mapping at the same time in blocks. And then we can have the parallel extraction. So as you can see, is the same. We have sequential input and output, and then we have parallel and output on the bottom part, while the GPU is training a particular part of it. So it's even better because it doesn't get into an idle state. Okay, so basically, I don't know if this has the comments. So what we're doing here is that, as you can see, we're loading the data, right, from storage. But now we are saying, okay, this is the number of parallel reads that I want to execute. Then on the map line, you can see that we can also define the number of parallel calls. And then we define the batch, and the prefetch, we can set the buffer size as well. And that, again, is pretty useful, depending on the size of your data. Sometimes you don't really need this. So continue talking about the TensorFlow extended pipeline. Now we're going to talk about the TensorFlow transform. So we have a way of working with the feature columns, right? So for example, if we have a numeric, the numeric one, we have a number, and we're going to have one element vector for that number. Then we have the categorical one. So let's say we have red, green, blue, and we have one hot encoding. We can also place like a bucket size. So we place we have a number, and then we do the conversion to to certain tags, and then we put it into the buckets. Then we have the cross one. So let's say we have different categories. We have red, green, and blue, and then we have for the size M, L, and XL. So what it's going to do is that it's going to cross them all to have all of the different combinations. So for example, red M, red L, red XL, and then so on and so on and so on with the rest of the colors. And then it's going to do, again, by M categories because of the number of the ones that we're going to have. And then it's going to be encoding for that. Then we can embed many categories. And then we have the hashing, that we can use that for infinite categories. So for the first one, we can work with vocal list and files or identity, bucket size, partition by range. For crossing, we can capture feature interactions because they're related. For embedding, it can learn new representations, and for hashing, we can limit the bucket size. And this is for categorization, and this is for numerical representations. So for example, we have the linear scaling, and this is when we can use it when the data is more or less distributed in a uniform way across the fixed range that is set. Then the clipping, it allows us to handle the very extreme outliers on the data. So we're going to see some examples in the next slide. Then the log scaling, and this is when the data is skewed by the power law, so it can go way up. The set score, and this is to handle the outliers that you don't need the clipping because they're not really very extreme, but still you need to handle them. So let's have a look at that. There on the first box, that's how we get the feature, the data for that feature. And then we're scaling to a range. So if you can see the X axis, the range is different. So we might want to range, and with that we can scale it to that particular range. So that's pretty useful. Then we have the clipping. So if you see, what we want to do is to the maximum values that we have on the x-axis and the y, we're clipping them to be part of a specific range as well. So let's say one that we have on one of the values, we can move it to the next one. So that's how we do the clipping. And if you compare, you will see that they're different. Then we have the log scaling. Again, we want to use the log scaling. And then the set score, that is, again, to deal with the outliers, but not for the extreme outliers, if that makes sense. Okay, so where do we do the feature engineering, which was stuff that we're talking about? So there are three possible ways. So each of those ways has its pros and cons. So let's have a look at that. So we have, let's say, the inputs. We do some pre-processing. We create the features. Then we pre-process the features, and then we train the model, and we by the end. If we have the input, also on the step one, we have TensorFlow. So it's going to be efficient, right? If we use it on the model, right? If we do the feature engineering there, is more efficient, but we just can use the TensorFlow methods only, and only for that particular input. Then if we do it during the feature creation, we use TensorFlow transform. It's very efficient. We can use the TensorFlow methods only, and it aggregates. And then on the pre-processing, it can be used with Beam and Dataflow. The downside is that it has to be done in the pipeline, but we can use Python and Java code, and it deals very well with when you're using time windows. Okay, so let's imagine a model to predict the length of rentals. So we have the station name and the start date, right? So we do let's say that we have only that information. Maybe we have a CSV file, or maybe we're going to load it from a database, and what we're going to get is the station name and the right. So we're going to transform that input data, and we're going to get all of the features that we need for the model. So we're going to get the station name, and then we're going to work with the start date to take the day of the week and the hour of the day, right? And let's suppose that the date has a proper format, like the date and the time. Okay, so we extract those three features and we fed them to the machine learning model, and what we're going to get as an output is the direction, the prediction of that particular rental. So who does the transformation during the prediction? So again, if we see we get the input, we're doing the pre-processing, like we said before. Okay, we have maybe two, let's say, fields from the database, and we want to extract the features. So then we go to the step of feature creation. Then we're going to train the model, and then we model we want to deploy it, right? We serve the model and we do the prediction, okay? And ideally, we can call with the input variables and offer it to the clients, right? So ideally, the client code doesn't have to know about all the transformations that were carried out, right? They don't need to know, for example, that we want to take that data and from the date we want to extract the date of the week and we want to extract the hour and then we want to show it. So the client code, right, that is the one that is being consumed, has to be ideally would be the same as the inputs, right? So from the inputs, if you remember, we're getting the station name. It has to be transparent for the from the code that was doing the transformation. So we will do like a yeah, we want to fetch the information just given the station name and the data, and we should be able to get everything back. So transform ensures that the transformations are automatically applied during the machine learning predict, right? So if you can see there on the like we saw before, we don't really want to use our features for the client code. What we want to do is use the input data, right? That we got from the beginning for the client side. So as you can see here, the query is, okay, I want to predict using this model, using the duration and the start station name and the start date, and that's it. Okay, so in terms of flow, uh, the transformations, we should do it in lambda layers so that they're part of the, so in that way, you're moving the machine learning model to production. That process is going to be much more easier if you keep the input and the features and the transforms separate. It's going to be so much better. Yeah, this is basically what we discussed before. The transform pattern, the model graph should include the transformation again. And yeah, here are we saying like the same process that I explained. Okay, so let's have a look at some sample questions review. So, well, I'm gonna let you read the information. So you have to think about how should be what can be the best way, what is the best that will allow the model to learn city specific relationships between the rooms per person and the housing price. So if you can think about a solution. And yes, that's correct. The D is the best one because we're going to have all of the different. Is the best set of features for that model. All right, so that's the end of the presentation. Write your comments, questions on the Slack channel. We are going to be around, and thank you for your patience today.